Hi, welcome to the webinar. My name is Rich Stromberg. I have spent several years working on renewable energy projects across Alaska, both on the statewide grid and in remote villages with isolated microgrids. The expected outcomes for this webinar are to increase your knowledge on barriers, challenges, and solutions that are unique to extreme cold weather climates in high latitudes. During this webinar, we will cover these topics: characterizing the electrical loads consumed by the energy system, evaluating the energy resource available at a particular location, using both analytic and field measurement tools, some practical considerations related to transportation and installation of wind turbines in typical Arctic communities, effects of ice accumulations on wind turbine blades and instrumentation, some of the challenges associated with scenarios where wind energy makes up a large fraction of the total energy supply for a local grid, and the importance of community engagement and environmental impact assessment throughout all phases of a project. We'll close out the webinar with a summary level review of the more critical items that we've addressed. Let's start by taking a look at a map of Alaska. Alaska is very large as seen by the scale of the insert image. There are few roads and rail lines in the state, and the state electrical grid is even smaller than the road system. There are more than 200 remote communities in Alaska, not all of which are on this map. These are largely dependent on diesel generators and have some of the highest electric rates in the nation due to the cost of transportation fuel to these locations. These standalone village microgrids typically serve 300 to 450 people with an average load of about 200 kilowatts. Hub communities such as Nome and Bethel have a few thousand residents and average loads of a few megawatts. These communities are at the forefront of finding innovative energy solutions to offset their exorbitant energy costs and to create more secure and reliable energy sources. System electrical load data lets you compare when you use energy with when the local winds produce energy. How well do these factors match up? This data can also help you identify ways to use your energy more efficiently so that a leaner, more cost-effective wind solution can be developed. You may also identify problems with the current system that should be corrected before building your wind system. Quantify existing power outages, variation in demand, reactive power loads, unbalanced phases, voltage and frequency control are critical to understanding in addition to just knowing your average and peak power demands. And since you're collecting wind data for a year longer anyway, you might as well be collecting power data at the same time. This graph shows the hourly electrical consumption in blue for a remote village of 200 people. Wind energy production from two 100 kilowatt turbines is reflected in green, and excess energy, more wind energy than the community needs at the present, is represented in brown. Zooming in shows greater detail of which hours have excess wind energy. Your system design should account for this excess energy with energy storage, secondary dispatchable loads, or wind turbine curtailment to prevent power outages, power quality problems, or unused energy benefit for your system. Hourly electrical data is the minimum necessary resolution. A 10-minute or better data is preferred to model against your 10-minute wind data from the Met Tower. This increased data resolution does not cost any more to collect with most available power monitoring systems and will not slow down the modeling tools in any appreciable way. A system to collect electrical load data from a typical Alaska village with a diesel generator connected to a 600-volt power plant plus a peak power output of 480 kilowatts starts at about $700 and can be installed by a local power plant technician. A larger system with peak power of 1,200 kilowatts or 1.2 megawatts would start at $1,200 or more. Several vendors offer systems that can be configured to your community's power system to collect the best possible data at the most affordable price. Budget around $2,000 to meet all your needs. If there are large energy loads in your community that are self-generating their own electricity, like fish processors, logging mills, mines, it is important to instrument these electrical loads as well in order to evaluate whether a combined power system is the best solution. Now we move on to site selection criteria. This wind resource map is based on a combination of satellite imaging of terrain vegetation and surface roughness, a digital elevation model, high altitude wind data, and ground observations from airport weather stations plus previous wind resource studies, or MET towers. Over time, Alaska Energy Authority has been able to validate the accuracy by region of the wind resource model against actual measurements from installed MET towers at 30 meters, 50 meters, and some even taller.
These are the locations of currently operating community-scale wind projects in the state. Note how they align with the wind resource map on the previous slide. Turbine icon size roughly correlates to project size with 44 megawatts of rated wind capacity on the Railbelt Road System, 14.73 megawatts in the 3 hub communities of Kodiak, Kotzebue, and Nome, and the remaining 8 megawatts of wind distributed across 25 smaller communities.
The wind resource model is our first step in selecting a potential site. Sites close to the community are preferred if the wind resource is sufficient. Otherwise, look for a site close to existing power lines or roads. Greenfield sites are the least preferred unless they offer superior wind energy to offset higher costs of development, roads, transmission lines, site communications. Determine how you will transport and erect a 30-meter or 50-meter MET tower at the proposed site. Don't choose a site just because it was easy to drive a truck to with your MET tower in the bed. The data you collect may be a waste of your time and money if you do that. Taking the effort to hand carry pipe sections up a hill can be worth it if you see that putting a road into the site is feasible and warranted in the long term. In this example, wind turbines were eventually installed on a hill just beyond the left end of the road seen in the left image. A basic 34-meter meteorological tower weighs 1 ton and costs around $10,000. Transportation and labor to install the tower can be another $10,000 or more. A typical system collects 10-minute average, minimum, maximum, and standard deviation wind speed along with wind direction and air temperature for 1 or more years. The data card should be pulled at least monthly to ensure that the instruments are operating correctly and prevent large data gaps, which add uncertainty to your proposed system modeling and design. Multiple years of data collection increase the reliability of your wind energy assessment as weather patterns can vary from one year to the next. Try to site the meteorological tower as close as possible to the planned wind turbine location. The greater the terrain variation between the MET tower and the actual wind turbine sites, the less accurate your extrapolations of wind energy production will be as you move your development site away from the original MET tower. More effort to get the tower and equipment to the likely turbine site will pay off with more reliable data for modeling your energy system. Don't be tempted to set up your MET tower next to a road out of mere convenience.
Another important factor is the impact to local bird populations. Siting within a half-mile of a raptor nest, half-mile of a shoreline, or between bodies of water where fowl fly back and forth risks injury or death to species that have a right to exist and that we may ourselves rely upon for our own existence. The early forester Aldo Leopold asserts that if a species naturally evolved within an environment, it is most likely a necessary part of that environment, even if we're smart enough to understand how. Please consult with your Fish and Wildlife Agency when selecting MET tower and wind turbine sites. One final consideration in MET tower and turbine siting involves a species very dear to our hearts, people. Turbines and MET towers pose an unlikely but potentially severe risk for failure or collapse. In some cold environments, ice throw is a risk. As the typical collapse zone safety perimeter is 1 1/2 times the height of a structure, it is recommended to site turbines and MET towers at least 3 times the height of the structure away from occupied buildings to allow for extra safety margin. Another factor that can cause discomfort in people is the flicker created when the shadow from a spinning wind turbine blade is cast on someone's home. In the northern hemisphere, siting wind turbines south of town within 1.4 kilometers creates conditions necessary for annoying or disturbing shadow flicker. Beyond this distance, the sunlight shadow line is so diffuse as to not be detected. In this image, we see that most homes will see no flicker, and those in the purple will experience less than the maximum recommended 30 hours per year of shadow flicker. If possible, site turbines north of town or farther than 1.4 kilometers from the nearest home or building occupied during daytime hours. When setting up your Met tower, the anchors need to be able to keep a 2,000-pound tower standing securely. This can be a challenge in tundra where the active layer thaws as deep as 6 feet into the permafrost. Weak anchors can pull out in the summertime. For the image on the right, a Met tower was erected at an old logging site. In some places we encountered hidden voids where stumps and roots had been ripped out and recovered with overburden.
For sites with costly deployment or logistical challenges, a 10-meter tower study is a low-risk approach to determine if the site might be suitable for a more expensive and complete later evaluation using 30-meter, 50-meter, or taller meteorological towers. These towers are for reconnaissance-level data only. Large Met towers will be needed to produce data suitable for community and utility-scale wind energy projects. 10-meter towers can also be placed concurrently with taller towers to evaluate other nearby sites by correlating the wind characteristics back to 10-meter height instruments on the main Met tower. There are many factors to your wind regime that can impact the viability of your site for a wind project. Which months have better wind? What time of day will your turbines produce versus when is their load demand on your electrical grid? From where do the predominant winds originate, and how does that affect how you should place multiple turbines? As you go up in tower height, are the winds strong enough to warrant the extra expense of a taller tower for your turbine? Is turbulence at your site higher than the turbine manufacturer's allowable spec? The shape of your location's wind distribution tells us how one model of wind turbine might perform better than a different model. Here we see the power curve for a 100 kilowatt turbine and power production estimates over the course of a year based on factors from the Met Tower study. And here's the power curve for a 900 kilowatt turbine and power production estimates over the same time period. To make the best decisions for your wind project, all of this data must be collected, analyzed, and modeled. Money spent during the design phase will ensure your system produces benefits and meets the expectations of your community. Fuel, equipment, material, and supplies of any appreciable size are normally transported to remote communities by barge to minimize cost. 5 major barge operators serve coastal and river communities throughout Alaska. Air transport costs are significantly higher. The same factors that drive the cost of shipping fuel to remote communities also drives the cost to mobilize energy construction projects. Shipping diesel fuel and heating oil to the village of Akiachak on the Kuskokwim River requires a one-way trip of 2,000 kilometers, although this same barge typically serves more than one community along its route during any given voyage. Shipping to Marshall on the Yukon River from Anchorage requires a barge route of 2,500 kilometers. Note that a barge will stop at multiple villages along this route too. Shipping to Selawik from Anchorage requires a barge route of 3,000 kilometers. Again, a barge will stop at multiple villages along the route. It is key to remember that barges get scheduled early in the year. There may or may not be excess capacity in the existing barge fleet and scheduled to deliver construction equipment and materials to your project site, so plan early.
Climate change has caused lower, less predictable flow on the upper Kobuk River to the degree that barge delivery of fuel is no longer feasible. Fuel costs have risen sharply because diesel and heating oil must be flown in at air freight rates. You need to know the weight and dimensions of cranes and other construction equipment, turbine blades, tower sections, and nacelles, and whether they are compatible with the capacity of available barges and cargo planes. Will foundation materials be mined on-site or shipped in? Do you need a special barge or plane chartered to meet your construction schedule? What time of year does the route open up, and when does the ice return to block your path? For communities without barge access, air cargo capacities greatly limit the size of wind turbines and cranes that can be shipped in. Unfortunately, smaller turbine sizes may not meet necessary economies of scale.
Shifting to cranes, knowing which models are available in your region is important very early in the project design. This Kobelco CK850 is a crane typically used for the installation of 100 kilowatt wind turbines in Alaska. The crane weighs around 53 tons with an additional 28 tons of counterweight that need to be deployed to the construction site. Here is the Kobelco CK850 and a Northern Power 100A model turbine in Tuksuk Bay. This is a Clark Lima 300-ton crane, model 7700, and an EWT direct wind 54 turbine in Delta Junction. While this larger 900 kilowatt wind turbine provides better economies of scale, it also presents significant challenges with transporting the crane to remote locations and with maneuvering the crane from the barge landing to the wind turbine site. The crane itself weighs 180 tons and must be compatible with transportation options to the site. Large barges are typically used on the mainline routes, while smaller landing craft may be used to transport material to shore or to navigate shallow, narrow waters. The image on the lower left shows tower sections for a 100 kilowatt turbine being offloaded at a remote village. The image on the lower right is a barge delivering GE 1.6 megawatt turbine blades and tower sections to Fire Island near Anchorage. On select projects, short ice roads and skid strategies have been applied to move turbines and construction equipment to the site. You'll be moving some very heavy equipment and materials across the terrain. The winter of 2013 and 14 in the Bethel region was notably warmer than average. You can see here the table on the left. This would impact any construction project that relied on completely frozen tundra prior to deploying heavy equipment across the terrain, as it would take longer for the entire active layer to freeze back from the summer thaw. Eventually, warmer temperatures will increase the depth of the active thaw layer in the summertime. Warm permafrost in the lower Yukon-Kuskokwim region poses a significant threat to long-term wind turbine foundation integrity, and the long-term ground temperature trend is on the right. And you can see it's risen about 1.5 degrees Celsius since 1950. In a typical summer, an active layer of around 6 feet deep melts and then refreezes in the wintertime. A key goal in Arctic foundations is to keep the soil frozen where the foundation is anchored. This could become challenging over a project operating lifetime that can last 20 years or more. Here's a common wind turbine foundation design in Alaska. With permafrost, construction is typically done in the winter. An oversized hole is pre-drilled large enough to fit both the pile and the thermal siphon, approximately 9 meters deep. Thermal siphons are located at each 0.406 meter diameter pile for this 100 kilowatt wind turbine. Current passive technology only allows for cooling of the foundation when the thermal siphons encounter subfreezing air above ground. Research is happening with summertime active cooling systems that would be powered by solar PV modules. Here is the as-built foundation for the Quinhagak 100 kilowatt wind turbine. As the climate continues to warm, the active layer will encroach deeper into the soil than the current 6 feet and take longer to refreeze in the winter. The deeper active layer changes the moment arm or lever arm force on the combined wind turbine and foundation structure. Think of a deeper thawing layer as creating a longer arm on a lever by which the lateral forces of blowing winds create greater force on the anchored portion of the wind turbine foundation. Shifting to what happens above ground, many sites in Alaska can experience frost and ice. Here we can see rime ice on Newton Peak outside of Nome and the resultant collapse of a meteorological tower. As moist, supercooled air rises from the coast toward the hills north of Nome, ice condenses on structures and increases the total mass that the structure and foundation must support. Heavy rime ice can stress guy wires and other structural components to the point of failure, which is what happened to the Met Tower on the right. Heavy rime ice and even light hoarfrost can build up on the wind turbine rotor and change the aerodynamic lift properties of the blades. This example isn't a structural problem, rather a turbine performance issue. Here we see hoarfrost has accumulated on the trailing edge of an EWT direct wind 54 turbine blade that will diminish the power output of the wind turbine. Here are wind speed trends from two 900 kilowatt wind turbines above Nome. Uphill and downhill wind turbine ice-free anemometers are seen during an icing event on Banner Peak, a site which is prone to heavy rime ice. Rime ice is accumulated on the uphill turbine faster than the ice-free sensor can melt it away, causing its anemometer to read slower wind speeds than the downhill turbine. Hoarfrost is lighter and would normally not accumulate on a heated ice-free anemometer like you see here. And just to go into a little more detail, the graph on the right is a zoom in of the graph on the left, and you can see the dark blue line is the uphill wind turbine's anemometer that is showing significantly lower wind speeds because it is icing up at such a high rate. This is the Nome EWT 52 turbine number 1 showing overlaid power curves for non-flagged normal periods, which is the blue dotted line. Met tower icing events are the orange flat line along the bottom. Pre-icing reduced power production is shown in green, and post-icing reduced power production is shown in yellow. And then there are some other possible events where no Met tower icing was observed, and those are the gray dots kind of in the middle. The wind speed along the horizontal axis is from an ice-free anemometer on the nacelle of the wind turbine, whereas the presence of frost or icing is determined by a nearby Met tower with non-heated anemometers. Not only is the wind turbine power output reduced at times where the Met tower instruments detect icing, the orange values at and near zero energy output, but diminished power output is seen both before and after the Met tower was able to detect icing, suggesting that ice and frost can build up on wind turbine rotors sooner than anemometers and take longer to melt or sublimate off. So not only can ice and frost impact the power performance of a wind turbine, but heavy rime ice will increase the load on the rotor and drivetrain, which could affect the turbine lifetime. Rime ice can also cause damage during shedding if the rotor is spinning.
On large power grids, wind energy contributes less than 10% of the total energy across the U.S. or Europe. Even though a state or country may boast of achieving 40% or higher wind energy, this energy impact is spread out over a balancing area that includes neighboring states. Village power systems are on isolated grids and have nowhere to spread out the continually varying wind power and have to consider the challenges of between 20 and 50% wind energy at any given time. These medium and high penetration wind energy projects require significantly more complex design and operation strategies.
So using wind turbines to power lights, motors, and pumps has greater economic benefit because it offsets 35% efficient diesel generators with 100% efficient wind power, so around a 65% benefit. Excess electricity has less economic benefit because it offsets typically 80% efficient heating oil boilers with 100% efficient electric boilers, so only a 20% benefit. This graph shows that higher average wind systems on the x-axis will generate higher amounts of excess electricity, shown on the y-axis, that must be accounted for in your system design. The graph assumes diesel gensets that run at a minimum 15% loading, and there's 30% minimum loading. If that's what's required on your system, that would reflect higher excess electricity. Returning to this earlier graph, we see hours where there's excess energy, shown in brown, that must be considered in the system design. During the conceptual design phase of your project, you need to decide how to respond to these periods of excess. Will you curtail or turn off one or more of your wind turbines? Do you have secondary loads such as electric boilers, baseboard heating units, or dispatchable pumps that can be turned on and off as this excess wind power fluctuates? These dispatchable secondary loads are essential to ensure that your power grid maintains voltage and frequency control. If you can't add enough boilers or other heaters as value-added dispatchable loads, electric dump loads will be required. A few other things to consider as we wrap up are that wind energy is not a panacea. Setting unrealistic expectations can result in a dissatisfied citizenry and a negative impression of wind energy. This community will be looking at these wind turbines for decades. When they do, will they see them as monuments to success or disappointment? Local people will need to be trained to maintain and troubleshoot these systems. Power systems require constant upkeep. Early and continual involvement by the community is necessary for long-term success. Lastly, wind energy systems must integrate with the environment, not compete with it. An energy system that reduces electric rates but disrupts the local animal and plant life cycles will create other problems for your community. Here we see muskox grazing beneath the Banner Wind Farm near Nome. To wrap things up, upfront planning is critical for enabling the success of high-penetration wind systems. Understand your system requirements, available resources, logistics options, foundations, and the key parameters of your wind regime. Identify and address your constraints. Then develop a detailed conceptual design within these constraints and parameters to determine if a wind project will meet your needs in an economic manner. Installing a wind turbine is relatively straightforward. The challenges are in the integration of the wide range of energy these systems produce. Addressing all the intricacies of integration during the design phase of a project ensures the maximum benefit for your community. In-depth engagement with the local community throughout each step of the project, from initial concept through decades of system operating life, are critical for ensuring the project meets local needs, will be accepted and supported, and will be sustainable in the long run. Careful assessment of possible impacts on the natural environment early in your design will avoid difficult decisions later. Many problems can be identified by consulting with Fish and Wildlife personnel during site selection and making minor adjustments to turbine location, height, and marking or lighting.